when you're working on a problem, try to think of ways to try to think of what is the scientific way of solving this. You can think of yourself that you're already a scientist. You don't have to tell anyone that, you don't have to say to anyone, but tell yourself that you're a scientist and how would you solve this problem. Try to find problems in whatever you're thinking.
Hey guys, today we've got Amitabh Yadav with us, a research fellow at CERN. Amitabh did his bachelor's in electronics engineering and even got an internship at CERN right after he graduated. Pretty impressive indeed. While working at CERN, he realized how much potential electronics had in physics domain. So he went ahead and did his master's in computer engineering from Delft University of Technology. Now he's a part of the team pushing the boundaries of particle physics. We are super excited to chat with you today, Amitabh, and we want to learn a lot from your experience and journey.
Well, thank you, Shruti. I'm really excited to talk as well. I'll be glad to help out with any queries that you guys have. Like, hopefully, some of it will be interesting to learn about, and like, hopefully, some of it will help. So, yeah.
Rimsha, this is not a college fest, so you could have been way more informal with the introduction, but yeah. Anyway. Oh, I mean, Shruti, yeah.
Yeah. Okay, so let's start from the beginning of your journey. Why did you particularly choose to do engineering in electronics, and why not in any other field?
So it was my school days. Actually, I was very much interested into pursuing computer science. I was good at programming, and at some point I thought that, okay, this is interesting, but I feel like I can do a lot of this on my own. And like, what I was more interested was to look a little bit deeper inside what goes on inside a computer. So I was more interested in the circuitry and how the processor is able to perform. And like, also my family, my dad was an electronics engineer, so I had kind of an early introduction to electronics, and that basically drew me to choose the subject. Like, when I went for counseling, I remember I had a couple of options, and it came down to basically these two, either computer science or an electronics engineering. And I felt like, yeah, I should go ahead with electronics, although I was not sure what I'll be doing afterwards. So I literally had no idea.
Yeah, pretty awesome. So speaking of interests, like most of the students in India in their bachelors, like engineers, half of them are preparing for GATE exams, and half of them, like the pure sciences one, are preparing for JAM exam. So in that scenario, what do you think how important it is to think out of the box in your bachelor's degree, like do different projects or do courses out of your framework, network from the different people, some people already working in the field? How significant it is?
So it varies. At some point during your bachelor's, you'll have to figure out what you want to do ahead. And like, basically, I would say the first and the second year are probably the best times to just explore around what is being offered by the university. Maybe talk to your professors who are running a lab. For example, robotics lab was one of the labs that I was really interested in back then. So and then somewhere around, I think at the end of second year or maybe third year, you can decide on where you want to what do you want to pursue after this. So if you're into GATE, then yeah, either way, I don't think it doesn't matter. But if you want to pursue GATE, or if you want to pursue GRE exams for higher studies, or whatever you want to do, the key is to basically start a little early. Usually in the first and second year, we are a bit exploring the college life, and also that's also very important, actually. But it also is important to just keep a bit of a bit of grip on your academics, and because if your scores are low, it can harm you in the long run. I'm not saying that you would not be able to make it or anything. You will definitely make it, but it will be a tougher road. So do yourself a favor, like just pay a bit more attention towards academics, and that will help you on GATE as well, and also on GRE. And then like if we come down to the projects, the kind of projects that you can do is, first of all, for me, the earliest introduction I got was basically on the fourth day of my when I came to the hostel. My college even hadn't even started, and basically at my hostel there were some seniors in electronics, and we just started chatting, and they showed me what they were working on. They were third year students, and that's how you basically talk to people and learn what they are doing, and they would rather help you to get some idea. So you can go and do some technical projects with professors, or you can help out your seniors in third or fourth year, like what they're working on, and if you can like assist in any way. So that definitely helps build your profile. It wouldn't matter so much for GATE, but yeah, it can create a huge difference if you're applying abroad, for example.
So speaking of projects, could you tell us about some of the most interesting projects you did during your bachelor's, and what were they related to, what were they focused on, and how did you come up with those ideas for those projects?
So yeah, like I said, like my introduction to working on projects started a bit early, and that was all thanks to my seniors in my hostel, that they just showed me that, yeah, this is, for example, a PCB, and these are the microcontrollers we are using. So back then we are using a microcontroller called Atmega 32. So it's even used at our labs that I'm currently working in. We don't use it like directly for the whole application, but we do use it for a lot of testing and debugging of different ports. So back then, Atmega 32 was one of the popular microcontrollers, and they just showed me how to work on that. And that just gave me a little bit of edge on how to program these microcontrollers. I basically had a small lab set up in my PG, and I just used to play around with different applications. So one of the first ones was basically creating a Land Rover, which can map the terrain, the unevenness of the terrain. So this was a geoscience project, which like some geoscience people were trying to use their software to map the terrain, and they wanted to create a robot that can actually do it automatically. And I was like, yeah, I can just create a simple. Back then, it's not something new. If you go to any university, you can find first, second year students building line follower robots and obstacle avoidance robot. It was basically that, and it worked great for this application. So I basically adapted something that I knew already to a different application. And one of the most interesting ones was taking the same microcontroller and adapting this to a different application. So one of the best ones was creating a wireless sensor network to predict landslide in the Himalayan regions. So my university was located very close to the lower Himalayas near Dehradun, and there was a project at the Indian Institute of Remote Sensing that was kind of interested in this, and we collaborated, and ultimately that led to a publication as well as a patent.
Nice. So now I'm going to ask you the question which you might have answered thousands of times in your life. Okay. How did you get into CERN? What was the procedure which you followed, and what do you think worked best for you in the overall application?
That's a good thing that you asked that, and I can actually be very very direct about this, because I know exactly what made the difference in my profile. This was, I think, towards the end of my internship, that I was just talking to my supervisor, and I asked him the same question, like, why did you choose me? And he was, and luckily he just told me what the process was. So before that, some context. When I first applied to CERN during my third year, and it was for the same position, the summer student position, which is sort of an internship. It wasn't successful. I think I applied to more than 50 places for internship, and I think the closest I got was at Texas Instruments, and ultimately they ghosted me. So yeah, no hard feelings, but I still feel bad about it. Then out of 50, I got one successful, which was at Bhabha Atomic Research Center. And I basically did it the old school way. I just wrapped my transcripts, my academic records, cover letter, and just posted it a physical copy to BARC, and they selected me. I think around March I received that thing. So that project was interesting. And then again, while I was studying during my third year and fourth year, I'd already published one paper, and there were three more projects in the line. So there were some national and international competitions were going on, and I was sort of working on that. And luckily, with a lot of hard work, and it was a lot of team effort, that we succeeded in all of the projects. There were three international ones and one national competition, and luckily in all of them we got a respectable rank, and two of them we stood first. So all of this basically helped me build a good profile. And towards the end of my fourth year, I wasn't even sure if I was eligible to apply to CERN, since I was finishing up. But I thought, yeah, it doesn't matter. Just apply. It's not my job to think about what they are thinking or how they will evaluate. I just sent in my application, and that was the thing that made the difference, that my academics were good, and plus I had so many different projects and practical experience that they could see that, yeah, I can handle a project there. And just to be one thing that is very important with CERN applications, they really look into what is your actual motivation to come here. So you have to be very original, you have to be honest, and there is no trick to being original, to be honest. The only trick is write whatever you feel genuinely. You cannot think about, maybe, yeah, this is probably a common reason. That's not it. If you're genuinely passionate about coming here, you will do your research, you'll find about experiments. So I was basically interested in one of the experiments called RD53, which deals with making these integrated circuits. And that project looked really interesting. So I basically mentioned in my motivation that, yeah, this is something I see myself working on, and I see that I can actually learn a lot from this. Yeah.
Great. So to summarize, basically, good academics, good practical experience, and a genuine motivation.
Indeed. I would say the priority is exactly like that. Your academics should be your first priority. If you can manage some time, work with your professor or your labs or your seniors, or if you can manage on your own, there are so many online resources. You can practically get everything at your home. I used to just take my whatever money I had, I used to put it towards getting these integrated circuit boards or fabricate my own. Circuit boards are something like this. If you see, I don't know if it's visible or not. Maybe it is. Maybe
Yeah, I can see. I can see. Yeah,
yeah. Getting a bit blurred.
Something like that.
Yeah.
So this is also one of the common ones. It's called ST microelectronics. This is a 32-bit microcontroller, and you can actually run a lot of things on this.
So in general, what does good academics means? Having a CGPA of 8.5 and above, like that?
Oh yeah, that's a very good question.
And one more thing, you said good academics should be the first priority. That's only when you're applying to the field that you're studying in, right? Let's say if I'm applying for physics, it may not be all that relevant. Would it be?
Academics will definitely be relevant, because that's the first threshold you have to cross in any sort of application. If you are appearing for a gate application, then you're appearing for an exam, right? So you can actually there is an exam to, even if you don't have so good grades, you can prepare later, and then you can write the exam, and you can score well on that, and then you have a proof that, yeah, you know what you have studied. But with universities abroad, or even during PhDs in India as well, they first look at what you have studied, because that is the most important thing. Your basics should be very strong. There's no going forward without your basics. As in, let me give you an example of this. That if you're hearing that you're okay at CERN builds Large Hadron Collider, and we try to find how the universe came about, and all of these things. But to be honest, we don't exactly tackle that question directly. Each department is concerned with doing one particular task, and when you go back to the basics, it's actually one project that has to be done from the very basics. So I studied, for example, digital and analog electronics in my second year and third year. So it was like a broad topic. And what I'm currently working on, basically using those principles to create something that works and can be applied uh, to the engineering that happens here. Now, the advanced part comes here, that when you have to optimize that design to meet certain constraints. There's, for example, a power constraint that your device should not exceed this power level. So, for example, if there is an electronics that you're developing for cryogenic systems, we have superconducting magnets, and you need to place some electronics in that region, or some electronics should work in a radiation environment. What would be the effect on your circuits, and how can you prevent them? So the engineers here, we develop, for example, radiation hard electronics, and most of it comes from packaging, but a lot of it is also design redundancy. So in design, you have to study those radiation effects and like try to interpret what would be the effects on what you are developing. So these kind of challenges, like the advanced part comes, that is more of refining what you already know, but ultimately you'll start from your basics. That's true for any field. I think Nachiket has something to say.
Yeah. So you mentioned that you were so you appearing as a summer intern, right? Summer intern. So you are basically like applying for applications. So all applications you can find about summer internship, you are applying for that. And were you like cold approaching professors? Were you cold mailing them?
Yeah, so for the internship, to be honest, I was not much aware on how things work, or should you write to professors or not. Luckily, I was not alone at my university. There were two other seniors of mine who had already done an internship here, which is called the Open Lab Summer Student Program. And they were both computer science engineers. So I basically got in touch with them and asked them, what did you guys do? And they told me some insight on what happens here, on how can you target your application towards this thing, towards the program. So for example, I still remember one of my senior, Shubham Gupta, was there, and he told me that CERN works a lot on supercomputing research. So you can probably target your application towards tools that are used for supercomputing. So I think if I'm not wrong, I think he told me to mention Hadoop and Spark. If you know that those technologies, you can mention that in your application, and probably, yeah, you'll get an edge. And I was not sure back then, but I thought that like CERN is an important institute. They probably are working with high-speed electronics, and I knew that FPGA is one of the most important things that you can use for this application. So my whole application was targeted towards FPGA. That, yeah, I'm an FPGA engineer, I can work on this and I can develop these kind of things, have this kind of experience. And it was kind of shot in the dark, but ultimately I found out, yeah, that is true. There's a lot of application of FPGAs here, and that is one of the things that you can start with. Basically, go through the websites. It's not just cern.ch. You can go to all these different experiments. They all have their own separate websites, and they publish what kind of work they do. So you can get a good idea on what kind of things are required to put in an application. As for cold emails, at summer student level, it wouldn't help much because I think CERN gets around 5 or 7,000 applications for summer studentship, and it is sort of, luck has a certain amount of thing here. But the best you can do is, yeah, just be original in your application and try to find as much as possible from the websites. If you think you know enough about the group, yeah, definitely you can write to them. It doesn't hurt your case. But for summer studentship, it wouldn't help much. For technical student program, which is a separate one, I think it's 12 plus 2 months. So 14 months program. So you can write emails to professors, but definitely do your research, what they're actually working on. It shouldn't be a generic email.
Something similar to this. Yeah,
Mhm.
sorry, go on, Nachiket.
So you are basically waiting for the perfect opportunity, waiting for that one like one advert they put out that, hey, we need this kind of engineer, and once you saw that advert, you jumped on it.
Yeah, mostly it works like that, not just here. It's kind of cliche to say this, but you'll have the best chance if you keep applying to as many places as possible. So CERN was not at all my yeah, it was not at all like if I don't get CERN, I'll be like I don't know what I'll do, so kind of thing. So I had applied to many other places, and CERN basically happened. Yeah, it it happened. So I had an easy decision to make that yeah, I want to go here. But the best thing if you can do is apply to as many places as possible. There are so many different labs in the world. If you are actually interested, for example, if you're a physicist, you're interested in particle physics, if you have heard of Stanford Linear Accelerator, that's called SLAC laboratory, it's very good. You can apply there. There's a Japanese accelerator called KEC. You can apply there. Then in Germany, there's, I think GSI is DESI, sorry. There's one experiment called DESI. You can apply for that. There are many experiments in Antarctica as well. So if you're interested in exploring dark matter and want a vacation in Antarctica for a couple of months, they are definitely apply for. I think it's called DUNE, Deep Underground Neutrino Experiment.
And by the way, when you said you've applied to a lot of internships and projects, how were you getting to know of all of these? How did you get to know?
So some of them were mostly shared to me by my seniors. So I remember there was this Canadian internship, MyTax, yeah. So I applied to MyTax as well, and in both in my third year, just in my third year, yeah. So MyTax was very interesting. Then in Germany, also there's a foreign exchange program, that kind of thing I applied for. Then there's a Bose Excellence Fellowship as well. Then in India, there was Indian Academy of Sciences Summer Research Fellowship program, applied to that as well. So all of these, like, I didn't leave anything. There was no stone unturned. And these days, the best tool you can use is Google. Yeah, it takes some time. It is a little frustrating, I know, but yeah, you can just find kind of fellowships or internships for summer studentship. You can find it on these company websites. A lot of companies these days are like very enthusiastic about giving more opportunities for bachelor students. And the best time is, I think, towards September to November. Yeah, especially for industry, they that is the window when they open up applications for internships.
Great. So something similar to your previous answer. What do you think particularly skills you developed it out of your regular curriculum, normal electronics, like for example, programming or something like that, which help you throughout the CERN program and to understand the projects better?
Indeed. Okay. During bachelor's, it was very interesting. As in, during bachelor's, I was leading a couple of teams, which gave me like a lot of management aspects. There was a deadline pressure that you have to deliver this a working prototype. Then you had to manage the finances. Our university was not like was a relatively young one, so it was hard to find like finances to manage us. And ultimately what happened was, like, we created a team that luckily everyone was very enthusiastic about what we were doing. We were trying to build a rocket for one of the competitions, and everyone was so excited, and we pitched in a couple of thousands. So I think we tried to tell everyone, like, so most of our juniors, we told them, like, please don't put more than 6,000 rupees from your own pockets. And ultimately, I think I ended up paying something around 25,000. And like, we tried to keep it less on students, but yeah, around 6 or 7,000 everybody pitched in. And once we had a good amount of money, then ultimately, yeah, we traveled all around the country. To be honest, like, most of the students were from different places, so we told them, we are going for winter vacations. Talk to the industry people there, try to arrange what kind of machinery they can lend us to to develop our prototype, and some of them they actually came through. There was one company called Endeavor Engineering in Ahmedabad who agreed to lend us their carbon fiber material. They lent us their CNC machines to build the whole prototype. So all of this thing was like super interesting. I'd never been to Ahmedabad before that, and then three of us. There's Dave, who was the team leader back then. I was leading the electronics side, and there was an aerospace guy, Aman. So the three of us, we went to Ahmedabad to just oversee and work on the prototype, and I think it took us a week. But we ultimately, all of this management was like super interesting. One of the things was like very interesting that I think this was something my supervisor told me during the summer studentship at CERN, that when you're working on a problem, try to think of ways to try to think of what is the scientific way of solving this. You can think of yourself that you're already a scientist. You don't have to tell anyone that, you don't have to say it to anyone, but tell yourself that you're a scientist and how would you solve this problem. Try to find problems in whatever you're thinking, and then you can actually reach to some solution. So all of these things definitely helps.
Wow, amazing. I think it's worth noting that you formed a team from students all across the India. Like you took many students, and how did you actually came up with the idea of that project, and how did you initiated it?
Okay, so the project was not something that we came up with. There's a competition, international competition. It's called IREC, International Rocket Engineering Competition. And it's a competitive one. You'll see people from all around the world. I think the Montreal University was one of the winners. But you can find everyone there, MIT, Princeton, everybody brings their rockets from the universities. And we saw that, why not? Like our aerospace department is a good one. Everybody has the expertise to do this. A rocket is a very hard thing to build. I would not underplay it. There are so many things that interdepend on each other that one thing fails and like it will be a cascading effect and everything will start failing. So it was a very big project, and like I thought it would be easy. Like there's one rocket, we don't even have to do the SpaceX thing. We don't have to recover anything. We just need to recover our payload. But still, just the launch part, just the monitoring part it's very taxing. And the students were everybody was from our university. Like our university had students from all over India, but everybody was enrolled in the university itself. So we didn't go about like asking for help from everybody. Yeah.
So you were just visiting the other places, present your thing, right? You said
we were all students of the same university, but yeah, everybody came from like different parts of India, right? There were South Indian people from Chennai and Tamil Nadu. They were from Gujarat, Gujarat has a good industrial complex. And basically when they went for holidays, we told them, yeah, you have this task, go around, talk to people and find us these kind of sponsorships, even if not money. We need resources to build this. We don't have carbon fiber. It needs carbon fiber was never in the plan. Like it is one of the expensive things to work with. But back then, the plan was to work with fiberglass, which is heavier, but it is much more affordable. But luckily, somebody in industry, they had a bunch of carbon fiber, and when we told them, okay, we are building a rocket, we'll take it to US, we'll launch it there, they got excited and said, yeah, you can use our carbon fiber. We won't charge it anything for that. So those kind of things, the negotiations has to be that is one of the skills that you can actually work with. So interpersonal skills, negotiations, how to talk to people, how to make friendships, how to establish relationships. So these kind of things is important even for in academia. Especially if you are in academia, you'll need funding at some point. If like that's a way ahead into the future, but yeah, those kind of things you can actually start working on like very early on. Yeah.
Great. So speaking of projects, like most of the students don't understand this fact that if you're doing a good project, just not approaching the professors and applying for the projects is not enough. When you're doing projects, you have to work hard for it. You're going to face a lot of problems. So on that note, I would like to ask you that what problems you faced in particular when you were doing project in CERN, and how were the roles the mentors and your supervisor played in that?
Yeah, that's a good one. It will happen a lot of the times. Not necessarily, even if you're doing research, there'll be a lot of open questions. There'll be times when you wouldn't have so much time to think about it, but you have to think about solutions to questions which you don't even know if there exists an answer to it, or if you are able to even define the question properly. And that is one of the things that comes with practice. The more you know about a subject, the better edge you'll have to basically to try to scout for any reason, or try to scout for any a solution. So the better informed you are on your basics. That's why I like keep the academics at the highest priority, and that comes with a little bit of experience as well. You see, uh, during masters I realized that, okay, whatever I'm trying to study, I it is built upon the bachelor stuff that I've studied. So most of the time I was actually revising my bachelor stuff rather than focusing a lot on the master stuff, because I could like basically derive from whatever I had studied already. So yeah, you need to be a little bit more informed. And the second thing that is very like kind of very easy thing to say, but it can often get very hard to do in practice. Ask for help. Everybody's there to like really help you. I remember this during my summer internship as well. There were some tools which were kind of basic to use, but I was like having a hard time to use them. And yeah, I just told them, my supervisor, hey, can you help me with this thing? And he hadn't developed that tool, but he knew the guy who had developed this tool, and he just gave him a call, and he came to my office, and like we sat together. He helped me understand this thing, and it's very like that. I remember the name of the tool. It's called YAR, and it was funny name, YARR. So yet another something readout. So it is literally, I'm telling you, these technology people are the funniest when it comes to naming things, because they're like, yeah, this is just another version of the same thing. So yeah, let's call it yet another something readout. So yeah, that was very interesting to yeah, ask for help, talk to your colleagues, try to find time for them. And that's also one of the interpersonal kind of things. Yeah, you can offer them, hey, let's sit at R1 and have a coffee and we can talk about something. And that happens all the time, by the way. Even here, like, a lot of these meetings are very informal. If you're talking to people from other groups, instead of saying let's schedule a meeting and we'll talk about this, we'll say, hey, why not let's have a lunch at R1. R1 is restaurant one here. So yeah, we just sit for lunch and discuss problems, what you are working on, what I'm working on, and so on. Yeah.
Great. So my next question might help us to do this transition from this undergrad level to your master's level. So how do you think your time at CERN influenced your decision to pursue your master's degree in computer engineering rather than going in the electronics field?
Yeah, that's one thing I correct everyone. I wish I could. I wish it had a different name. So there are two fields. There's computer science and computer engineering. Computer science deals with everything you see, like from cloud computing to softwares to distributed systems. Everything is computer science. Computer engineering is just one level lower, as in everything below compilers, OS comes under the regime of computer engineering. So that deals mostly with how you design processors, and that's computer architecture, how you design the digital system that deals with it. So as in the Boolean logic, or how you create circuits, or how you create algorithms from those circuits. A bit lower than that, how it comes, what happens at the semiconductor levels from transistors, and it's up to you, you can go lower. But yeah, everything below compiler. So that was my main interest. So even when I started my bachelor's, I had this curiosity on how computation happens faster, and it still remains my utmost curiosity. that how does some computer perform so much faster than the others. So computer engineering was like definitely, I remember I took 1 day off during bachelor's that, I'm sorry. Yeah, I took 1 day off during bachelor's. I went to this place called Forest Research Institute, FRI. It just has a good, really beautiful lawn. And I sat there and thought what I wanted to do in my life. And it took me a couple of hours, but ultimately I thought, yeah, I want to just go with the original idea. Let's explore how processes work, and how high-speed systems work. And that's what like inspired me to apply for this master program in computer engineering. And it was later that during masters I got interested in other things. uh, our masters in computer engineering had a specialization with quantum computing, and I was very much curious that how quantum computing is a branch of computing. It has less to do with physics and has more to do with computer engineering and information theory. So it was kind of an easy jump for me that, yeah, let's see how quantum computing works, because I already know how classical computer works. Yeah.
Yes, so what was your personal experience with quantum computing, since it's a very hype topic over the internet everywhere? So what was your experience with it? Like,
Yep.
is it the same thing the way people talk about it, or there's more to it?
I think in media, quantum computing is shown like it's the savior computing paradigm, which will accelerate everything. It will solve everything in parallel, which is on the technical terms speak. If I speak, that's not the case. The original idea came from like 1917 when 70s when there was a Professor Yuri Manin, and then Richard Feynman. These guys were just toying around with the idea that, well, nature is quantum mechanical, and if you want to simulate the nature, then we need to build a computer that works on the principles of quantum mechanics. And that was the original abstract idea. And somewhere along the line, these computing paradigms started developing. So Professor David DiVincenzo was the first one who actually created this what a quantum computer should, the criteria for a quantum computer to satisfy. So David DiVincenzo was actually at Delft in my master's university. So I met him as well. And all these people were like basically bringing to reality an abstract concept into a physical realizable device. So now there is a hugely, well, when we talk about quantum mechanics, and it is a very well-known fact that if you say that you understand quantum mechanics, you probably don't understand quantum mechanics, because a lot of rules are fuzzy there. And it is true, and you have to work all around that. So there is a clear division of labor. There are experimentalists who build these devices, then there are theorists, and then there are computer information theorists who work on algorithms and stuff. And I was more into developing the experimental side of things, on how can you realize a particular algorithm on a quantum computer. So definitely I studied how these qubits behave, how you can how they are manipulated, how do you bring one qubit to one state, and how do you read out that state, or how do you transform that state, how do you perform unitary transformations, which is basically applying some sort of operation on one qubit to create a sort of result. So there is a lot of technical stuff. It is not at all intuitive uh, to come up with a solution. It is sort of easy to understand any application, but like if you can understand Shor's algorithm, which is one of the most famous algorithms, you are sort of ready to jump into the applications. But it won't be easy. I mean, the applications are not straightforward. There is a way of thinking about solving problems. The original definition of algorithm is, as you know, how do you solve a particular problem step by step. All that very basic definition fails in quantum mechanics. When you apply a quantum algorithm, you're not going step by step. You're going in all the directions at the same time, or you are playing with some sort of things to expect that something else will happen. it's hard to even describe. As you can see, I'm having a hard time just to describe the inner workings. So it needs a solid foundation of your basics in information theory, in quantum mechanics as well. And the first applications that you'll see in quantum computer will be, for example, simulating quantum states of atoms, of creating these protein folding simulations, and there are many simulations that are in line. If you're like really interested, I would definitely suggest to look into quantum chemistry applications or genome sequencing applications. Those will be very interesting for the quantum community. Or even the combinatorial optimization problems. That is one of the like early applications. But it will never be the case that your desktop computer will be replaced by a quantum computer. That's not going to happen. It will be more or less like a supercomputing kind of thing.